Okay, hello again, everyone. So today's meetup, we have Erich Schudt. He's the co-founder of Bippit, which is a very interesting service. It's a financial coach for every employee. I'm interested in the the company itself as well. So when he founded the Bippit 2 years ago, he took a very big chance on Rust. From what I can understand, they have been using Rust in every part of the infrastructure, the code base, from logging, tracing, telemetry, tests, and many more functionality. So he's going to give us a talk about his experience with Rust in his company. Okay. Take it away, Eric.
Yep, thanks for that introduction. As you can see, I got my scheduling very wrong, so I'm actually in a hotel room, if that wasn't obvious. But that's fine. I can take some couple of hours off. I'm very excited to do this. So I have spoken at Rust London before. It's my first time speaking at Rust Dublin. So I'll just share my screen and then go through some of the slides I've prepared. Yep. So yeah, welcome to this talk on production-ready APIs in Rust. It's a journey with Bippit. So when I Googled the Rust logo to put on this slide, and the second one came up, which I thought was quite interesting. So I thought I'll put it here as well. It reminds me of when I first got onto the Rust discourse server talking about the Rust programming language. Maybe you've experienced this as well, but every now and again, you see random people come into the server asking about, oh, how can I build my base? Would you help me fight these people off? It's because it's a game called Rust, and it gets confused between the two a lot. So yeah, I'll be talking about the first one, not the second one. Although I play Rust the game also, very interesting, but not as much time on it as I do on the Rust programming language. The agenda for this talk, it's yeah, right on this slide. So a quick intro about myself and also about Bippit and what we do. The technical goals of Bippit when we founded it 2.5 years ago or so, because that mainly determines how you want to build it, what tools you want to use to build it, and if it is the right language and right tools to use to achieve those goals that you set out. So we'll go through some parts of it. I did want to go through every single part of this, but after I'm building out the slides, we'll be here all night. So I just picked out a couple of them. We'll go through the web framework, the database layer, and then I think event sourcing as well. And then if there are any questions or anything else, I'm happy to just address them. And also please just jump in when you need to ask questions about anything. I did want to go through a deeper dive into network calls because for us, that was one of our main goals and one of the things we thought would be very useful on our platform to build very fast services. And then finally, we talk about what we plan to do with Rust on our platform going forward. So about me, I started my career in Accenture, just working on a lot of software engineering projects around the UK, mostly in Java. I was trained in Java and built just a lot of features in it, and then started thinking about other languages, did some C#, some C, C++. I really like getting lower and lower to the computer level. Did some assembly as well. That was maybe a bit too low. It just took a lot of time to build anything. At Curve, I switched away from Accenture to work on more startups just so I can see my efforts and how it actually impacts the customer. And you move a lot faster as well with startups. That's when I started hearing about Rust and started discussing with my fellow engineers at Curve. And it was as low level as C or C++ in a way, but it doesn't give you that ability to just destroy everything. So with the type checking and everything else in place, you can do the things C gives you, but it's a lot less risky with it. So it got my attention straight away, and I started just exploring the Rust programming language from then on. Those two are my main resources that I use and when I first started getting into it. Once you Google Rust programming language, the book on the left is probably the first one that comes up. And I think most people have probably gone through that one. It has a lot of information on just a lot of different parts of the language. And it got me to a competent enough level But my focus was to build a microservice, and I had to follow on with the second book on the right, so microservice with Rust. And that was a bit more specific to my use case. So I was happy to use that as a resource also. And Tool Then Combined actually gave me most of the knowledge I needed to build up Bippit's platform. If you have read both of them already, then this talk will probably be a refresher course for you. So before going to the details, I always like to just highlight this tweet by Kelsey Hightower. He's a developer advocate with Google. He does a lot with the HashiCorp platform, which is what we use for our DevOps and tooling. I'll probably go into that a little bit, but he says that the thing you're trying to build should be more exciting than the tools you use to build it. So basically what you're building should excite you a lot more than how you're building it. And that's something I truly believe in. I'm probably in the minority of engineers who feel that way. But I do think that what you're building should be more important than how you build it. So I'll discuss a bit more about what we're doing at Bippit. You can tell this slide came straight off our sales deck. It's much nicer than the rest of the engineering stuff. So at Bippit, we're providing a financial well-being platform to employees as a employer benefit. So financial advice is very, very expensive in the UK and in Europe and probably in all of the world. You have to pay hundreds of pounds in the UK to talk to a financial advisor, and most wouldn't even talk to you unless you have £50,000 at least in your bank account, because they get money off of your assets under management. So by using technology, open banking, and a lot of other tools we have in place, we've reduced the cost so much that we can give it for free to the employee and through a financial well-being platform by the employer. That was a very one sentence description of what we do at Bippit, but you can go to our website if that sounds interesting at all, and just to learn more about it. We recently came off the TechStars program in Berlin. I would have really loved to go there and just hang out with all the 10 companies who were picked out in that program. But because of COVID, yeah, we couldn't make it. It was a complete remote accelerator, which was the first one that Berlin has done in a very long time. So what were the goals we did when we first started to build Bippit? Number one, we wanted a very reliable platform. Once you use it, you should barely see any errors at all come up. Every functionality should work seamlessly, even for the very minority of use cases and very edge cases. They should all work. Like nothing should come up with errors. This proved a bit challenging because open banking, which is an implementation of just in case this isn't aware, it's an implementation of the PSD2 by the EU, which pretty much means every account service provider should be able to provide their user data to anyone who has access to it, who has been given access to it. So if I have my data in my bank, say Santander, and I give permission to this app to just look through my accounts for me, Santander should be able to give all of my data to the app because I told Santander that they have my permission to do it. So that's one of the ways that we use to create to make financial advice a lot cheaper. So we get access to this data, we automate a lot of that process, and then we can just give advice at a very, very cheap rates compared to the current standard industry. But as if you've used open banking before, you would know it's not 100% reliable. It's at best 95% SLAs is what they have. So there's a bit of work to do there to make sure we still have a functioning service as much as possible. Number two, we wanted really fast services. The metric we use to measure this is that the 99th percentile for any API call should be less than 2 seconds. And that was very important for us. So a lot of decisions we made in terms of what crates to use, how to build it, was based on these two metrics specifically. And the third part, it should be extensible. So any features can be easily upgraded and extended to include just a lot of different services and functionality on top of it. And one thing I would like to point out is the use of ADRs, which are architecture decision records. They're used to document just any decision that you make on an architecture or technical basis. I would highly recommend that if anyone is deciding on patterns, APIs, architecture, that you use this just to record it, because usually 6 months down the line, you have no idea why you picked one thing over the other. And you probably think, oh, I probably wasn't thinking right. And then you go and switch it, and it brings this whole merry-go-round, or I'll switch back. But having this in place, you know, the different solutions you considered, the approaches you liked from one over the other, and why you picked one over the other. So we have ADRs for every decision that we've made from the beginning of Bippit. So it made it a lot easier to actually build these slides here today. So just a few of them that I'll go through about why we decided to use some crates instead of others, and when we built Bippit from the very beginning. So this is a roadmap of what we've done in the early days. So we started experimenting in Bippit at late 2018, just writing our Hello World service, mostly actually building the infrastructure behind it. So we use HashiCorp tools for our microservice-based architecture. It's a Nomad service for the orchestration, a Vault service for secrets management, and then a console for service-to-service communication as a service mesh. So that's mostly what was built in Q1 of 2019, and then the Rust services came on top of that. So we had our very first Rust service in production right before Q2 2019. And if you've played around with Rust and their SDKs that are available with third parties, you will very soon realize there's not enough out there for all the surprisingly very well-known and well-used APIs. So we had to build some of our services in Java just for that reason. The main one was Firebase. So we use Firebase for our authentication mechanism, but there isn't any SDK for Rust. So we had to create a different service in Java and then integrate all of our services with it when it needed to talk to Firebase. And this use case comes up quite a few times. Another example is with our analytics platform. So we use Mixpanel, and that also doesn't have a Rust SDK. Of course, you can always just communicate directly with APIs, but it also comes with a lot of challenges, especially around the authentication mechanism between our platform and their platform when everything is already inbuilt in SDKs. So again, we would just go ahead, and because it's a microservice architecture, we would build it all in Java or any other language where an SDK exists, and then integrate internally with our Rust APIs. So I would say at this point, about 90% of our services are in Rust, and that 10% is for any third parties we use that don't have Rust SDKs, and it just didn't seem like it was worth building a Rust SDK or integrating directly with their API. So we do use Risotto to integrate with some AWS services, and this is when we started thinking about event sourcing, but we didn't go into it in too much detail until 2021, actually, which I'll get to later on. Of course, there was the big async await upgrade, which meant a lot of changes to our services. And then in our goal to make things a lot faster, we introduce a connection pooling also to the database layer. We got to over 15 Rust services in 2020, and at this point, we're over 20 actually Rust services in production. So I'll just go through some of the crates that we use and why we picked one over the other. At the very beginning, we had to decide on what we use for our web framework. And there's school of thought was we would either go with a low-level crate, examples to the bottom left, Hyper or Request. Request, I guess you can call this low-level, but it's actually built on top of Hyper, but it doesn't give you too much. It's just a server and a client implementation. And then to the right, you have more framework solutions. Iron, which was the dominant one when we had to make this decision. I don't think it actually exists anymore. I think development has stopped on it. But there are others like Actix and Rocket and Tide and a few more. So these were the things that we're considering. If we go with a low-level crate, we can easily access the core functionality of things we want to do, that if we went with a web framework itself, we would have to wait for that to be included in it. Or you could maybe extend it and add it to it and then try and merge it back in, which creates just a lot of like development process on top of that. And also it's easier to just use the new features of Rust if it's a low level crate, because those get upgraded first. Because a lot of the other web frameworks are built on top of the lower level ones. I think every example I have on the right is actually built on top of Hyper. I might be wrong on Actix. I'll have to check on that one, but I believe they're all built on top of Hyper. So we ended up going with Hyper as our solution. It's the main reason, the number one reason for that was because of async await. When we started it out, async await wasn't in the in stable Rust. And we wanted to get there as soon as possible because we knew how important that was. Just writing code without it, it was just so difficult to read. And even for new engineers joining the project, it was difficult to understand as well. And we had to go through a lot of training process. So that was the number one reason to use Hyper. And as it turned out, Hyper was upgraded with async await about 4 months before the web frameworks were. So that 4-month period is quite a long time to have to wait once it was actually released by the Rust language at the time. I'll go through one more kind of scenario that we were thinking through when we started out. So we had to think about our database layer. What crate will we use to just access our DB? And same thing here as you would see with any other language. You could either go with the whole ORM solutions or with a native driver. In my experience, I've mostly been going with ORM solutions. This was in Curve and in Accenture, just because it's an easier model to map things. Once you create your model, you can have it easily map into your tables. It's mapped into your API models as well, and that integration, that syncing is very easy. You just save, most of them have like a save method, and everything is just synced simply like that. Whereas you have the native driver solution, and everything needs to be done manually. You write all the native queries, you have to build all your tables from scratch and write all the queries for every single thing. Of course, you can do it in ORM as well, but in ORM, you're trying to avoid that. And then in the native driver, you actually have to do all that. But of course, by using a native driver, they're really, really fast. One of the things we looked at was Diesel, which was an example of the ORM in Rust, against a native solution. And so we went with a Postgres DB. So we're comparing Postgres versus Diesel in terms of execution times to run these queries. And I don't have the link here, but Postgres was a lot faster using the Postgres crates compared to Diesel, mainly because Diesel did not support async at the time. So everything had to be synchronous when making calls to the database. I haven't looked at this recently, and the last time I did was a couple of months ago, maybe a year, but even then, async still wasn't in Diesel. I feel like they should have it right now. Otherwise, they're really, really behind. But if anyone can correct me on that, yeah, I'm happy to hear. But that was our reason for going with Postgres. But there's a second element to it as well. We wanted a connection pool, because with database connections, most of the time is, well, unless you have like really, really slow connections, but you're making multiple calls to your database usually, and just opening up a connection just to make a call or a few calls and then to close it just takes up a lot of resources, whether it's time or it's memory or CPU, just a lot of different resources. That makes it, that isn't very optimum. And it goes back to our goal that we wanted to create a very high performance service. You click on a button, you try and do something, it should instantly get the results for you, and you shouldn't have to wait too long, even for the very low minority like edge cases. And it's why we had to include the connection pooling to it. But before async 08, there was R2D2. So that would give you a pool of synchronous connections. So then that also went through an upgrade process of getting that from a synchronous pool to an asynchronous pool of connections. So Postgres together with BB8 builds up our database layer. Yeah, so I did leave out a couple of them because it was taking a bit too long to go through. We'll be here for a very long time to go through every single one of our decisions, but I'm happy to come back and just answer questions on the rest of our decision process if needed. But I did want to go through a deeper dive of our network calls because once we included tracing, we realized a lot of our time was actually being spent in this part of the system. And because it's a microservice-based architecture, you have a lot of different network calls happening within the system itself. It's why we were focusing on the network call. So in your typical LAMP server, which you probably wouldn't see anymore, you would have your database and your application server on the same physical computer. Of course, you wouldn't need any network call in this case. You just access it directly and then get any data you might need. Few people would have this use case anymore. This is definitely more standard right now. So you'd have your server sitting somewhere in the cloud, usually, and your application would just make a call over there, get some data, update some data, and then return that to the application server. The more services you have, the more this scenario comes up. So you have a couple of microservices, so like app servers in this diagram, sitting on physical nodes, server 1 and server 2, all making requests to databases to get data. With the number of hours, you can see they keep increasing. There's so many network calls happening between them. Once you get to 20, which is where we are, there's just so much happening and so much time spent on the network. And it's why we spent most of our time just looking at how we can make that process very efficient. So this led to our template Rust service, which is, I've gone through a detail of some of them, but just to go through all of it, we've pretty much built our own web framework on top of Hyper that uses all of these different ones. So at the very beginning, we used the Tokyo as the event executor. Of course, now Tokyo isn't really the standard anymore. You can have the standard async, but when we started, Tokyo was the only candidate. I'm still waiting for that convergence or maybe a higher layer on top of that where you don't really need to pick one of the other. You can just use either one of them. I think it has started, but it hasn't really happened just yet. So most of all of our services now are built on top of Tokyo. And as I mentioned, the main reason for that, it wasn't actually a decision to make. Well, just because we used Hyper, and Hyper is built on top of Tokyo. So Hyper acts as the application server and builds out also the HTTP clients just to connect to everything else. BB8, which I discussed already, so that creates an asynchronous pool of database connections. So you can just go pick up a connection, use it, and then put it back in the DB pool. So it never gets closed. It's always open, always available. You use it, give it back, use it, give it back. It saves just a lot of resources in that process. Tokyo Postgres as well. These are linked to auto crates, which form the base layer of our services. Risotto, which is very interesting. So at some point we realized HTTP calls are quite, it's interesting. So you can use it, and it does sort of synchronize your calls because you have to wait for a return and then you can finish it. But you want more event sourcing for some scenarios. This requirement came in a couple of months down the line. So we started looking at what tools were available. I'm a big fan of AWS. So it has both the SQS and SNS solutions, and when combined, can give you a very useful event sourcing solution. Not just in terms of like queue processing, but just combining the two, you can have things like sending out emails or pushing it into Lambda functions or even push notifications. There's just so many different use cases that can come up from just using those two solutions. So it made sense that we can build our event sources on that and then extend it when possible, when our more use cases come about. So if anything doesn't require a response immediately, they get pushed into an Amazon SNS queue, Amazon SNS topic. And then from there, it's all based on configuration of what you want to happen next. In terms of processing the events, they would usually go into an Amazon SQS queue, and that will get picked up by another Rust service, which is also built on the Risotto. So using the SQS module on that crate, it's able to just pull up any messages in the SQS queue, process it, and then go back and delete that message off the queue. And then some additional things as well. So Serde for JSON handling, it just seemed like the easiest solution to just, in terms of formatting of messages between any service at all, a JSON instead of using something like XML or just anything else. And plus, any third parties are usually in JSON as well. So once you build it internally, there's not much to do to integrate externally also. And then slog for logging or structured logging. There wasn't much competition also when we started. So this was the standard. And I still think it is the standard in terms of structured logging. But to include tracing as well, there is so much more solution. So our solution here was we would use structured logging, create our own type of properties. So a message ID, a causation ID, a correlation ID. And then that will be used for tracing across the entire network and infrastructure. There are much better solutions now. Things like, I think, OpenTelemetry, and there's a second one that I can't remember right now. But if you want to actually see a graph of your entire trace, something like Jaeger would give you that, using something like a structured log won't be enough. And it's the next thing that we're looking to do, not just having it in the logs, but being able to visualize exactly how the messages are sent across the entire estate. I think I will skip this part because no one writes code before async awaits anymore. But you can see it's very, very complicated before async awaits. You have a lot of either's left and rights and A's and B's just to make a call to an HTTP service. Yep, so we are async. And this is the code from the previous one. That makes it a lot cleaner. Of course, there's a lot of unwrapping, but it's just a test to show like how we focus our services to make like highly efficient HTTP calls and then to process that quickly. Because I think that was number 2 on our goal. Like it has to be really, really fast. So it just created a very, very quick client that connects to one of our services. I think you can actually see, and I don't know if you can see my mouse point, but if you can see the URL, which just points to our dev server, and then makes a call there. It creates the request body, it makes a call, sends it, and then it gets a body. And that's the get version code that's used by this this program over here. So you can see it's using the Tokyo executor. It calls the get version, which is the one I showed previously, and it has a duration and the result of it. It also calls the duration of the actual program itself. So the duration of the call is stored in duration 1. Duration of this program is stored in the duration variable. And at the end, it prints out the result, the duration, and the duration of the program. So this is just to show the kind of network efficiencies we got out of using Rust async await. So that's the result of running that program. So we get a version of the server. It took 170 milliseconds to make that HTTP call, and the program took 170 milliseconds to complete. Of course, that's just one call. So you would expect the program to be as fast as your HTTP call. Here's a slightly longer version. You're making 3 calls to the same HTTP client, which is the first code I showed to get the version. They're all done synchronously using async await. Same process here again. You calculate the duration and then print out the duration of the program. And this usually confuses a few people. So you are using async await, but it is running synchronously. So the duration of the program is pretty much a sum of the network call of each of the calls. So it's a synchronous call to each of the HTTP calls that were made. And it's because of the await keyword. Once you hit await, you're waiting for that to finish, and then you would continue. So we use a lot of different techniques, spawning combinators, to actually make use of async await and Rust green threads. So in this case, we are joining all 3 of them so that they're executed asynchronously, and then, as before, calculating the duration of this program. And then when you print out the results, the duration is equal to the maximum duration of any one of the HTTP calls. A little bit more just because the program is doing something extra. So this forms the basis of almost every part of Bippit's platform. Our services are mostly working over the network. And in order to get the best performance, we always have to make sure we are doing asynchronous calls when possible to get all the data we need and then return that to the caller. So you'd see a lot of spawning and combinators everywhere. If you just need one, you just select one and not wait for the other. If you need all of them, you join them all and then wait for that execution to finish and then put them all together. So what's so unique about this? You can get things like that in a lot of different languages. So what about Rust makes it so special? So the way I see it, there's 3 parts to it. There's that robust nature of the Rust programming language. You still get all of the error handling that you can get even without the network calls. You have to handle them. You don't handle them, it's your choice not to handle them. And if you don't, you are aware that you're making the choice not to do it. And then there's 0 cost to it. So with a lot of other languages, there's a cost to actually have threads, whether it's a memory or just anything else. And with Rust, it's a 0 cost to have this. But for me, the most important part of it is that it's a lot easier to write and to read as well. By using this, you can pretty much write asynchronous code as easy as you would write synchronous code. I'm not sure if you've been through this before, but in my experience, if you try to write some threads or try and make some parts of your program asynchronous, you're always told by someone else, another engineer on the team, that keep it as simple as possible. If you introduce threads or try anything else, you just make it more complicated and more reason to bring errors, which I think this eradicates that, and you can start using it as easy as you would if you aren't using it. So just these 2 lines of code, which is a cutout from the previous program, turns it into an asynchronous program. So it's literally just 2 lines to include, and then you get so much more from it. So you save so much more time by executing this. And it's what I like to understand as fearless concurrency. So you don't have to be afraid to just try and run these asynchronous programs. You can just do it by using very simple lines of codes. The takeaways we got from building everything in Rust. One, your API server is as fast as the amount of time you spend on it. All depends on how you architect it. I guess from our perspective, the way we architect it is almost everything is over the network. So once you've taken care of the actual query speeds of the data you're querying, And that's definitely the first thing you should look at. You shouldn't start looking at a network when your queries are taking a couple of seconds to run. It wouldn't make sense at all. So you first look there, optimize your queries, make sure you're caching when you need to, and all of these other things. And then you can start looking at how much time are you spending on the network to get all of that information. And then, as I mentioned previously, so you can use Spawning Combinators, and then you can reduce the time you spend on network calls a lot in your services. And it's really, really easy, especially since async await has come up, just to write these concurrent programs. So you should be able, well, I would expect to see them a lot more in Rust going forward, rather than just having synchronous code all the time. In terms of what worked very well for us, we had a lot of fun building it, especially at the very beginning when Rust was very, very new. You had to dig very, very deep into it just to understand what's going on, and then to experiment with so many different crates before you decide on using one. And you also have to try and guess or have some sort of speculation on what crates will still exist and what wouldn't. And if it doesn't exist, are you happy to maintain it going forward? And because there's a few crates that we use that isn't maintained anymore, and then we've had to take it and maintain them privately, although we're now looking to put that public as well, and push it back into the public domain. But that also takes a bit more like development resource and time, which is why we haven't done it just yet. But the goal is to get it back into an open source version of it as well. There's a lot less errors. So we push out every single error on our production service into our alerting systems. Slack is one of them, just so we can have a live view of exactly what's happening. And I think usually you would see, if you were to do this in any other company, you would see hundreds of errors every day, just because it does happen quite a lot. But by using this solution, by using Rust to build it, we barely see anything there. So every single error is pushed onto our alerting system, and it's barely ever getting alerts, just because you have to handle it. If you don't handle it, you know you're making the decision not to. And we have really, really fast APIs. I think this is a time snapshot, which isn't the best reflection on showing that how fast it is. So I will get maybe a longer time shot and put them maybe on Twitter just to show that as well. But the 99th percentile is for that snapshot is less than 400 milliseconds, which means that the slowest of the slowest of the slowest of calls was still like 400 milliseconds. Our goal was to get it under 2 seconds. So when we first saw this, we were extremely happy. It has gone up since. This is a little bit an older snapshot that I took. I will get a more up-to-date one and put that up. But I do think the 99th percentile is around 1 second for Bippit at the moment. And then, of course, we use very little resources. And reduced resources means less cost. If you're familiar with HashiCorp Nomad, you will know that that's how you would configure your service within a node. And these are our production configurations. So we just use about 64 megabytes, 250 for CPU, and we are running production service on this. So our costs, our infrastructure costs are very, very low, because you can pack these applications onto one node and then only have a couple of nodes, and we only have 3, and you can even use the cheapest of them, whether you're using AWS or which other provider you have. You can get the cheapest one and still pack a lot of into it. Of course, you want to maybe spread a little bit in case a node goes down. So you have a different node that has the application running. There's a lot of different considerations to make, but it makes it a lot easier if it's very small running services. It gives you a lot of options on how many nodes you need, where to pack them, and then it saves you a lot on your engineering budget to put somewhere else. And what didn't work so well? I think the lack of SDKs. That was something we noticed from the very beginning, and we still continue to see as well. If you're using a lot of third parties, usually they wouldn't do a Rust SDK as one of their first second, third, or even fourth options. And it's why I would recommend if not a microservice, there is this whole microservice architecture where you do have most of your logic on like a bigger service, and then you have tiny services that do more specific stuff. And one of them is usually just a different language as an SDK that wasn't available in the language that the main one is in. I think it's called a citadel approach, but I looked into that in quite a while. And then the lack of options for tooling. It took quite some time before we could actually find something to run to get a code coverage of our unit test. A lot of it actually makes use of unstable Rust, the nightly versions. And once you use stable Rust, your options go down by quite a lot. Tapolin was what we use for code coverage. And even then, there's so much that goes wrong, and you have to always upgrade to the next version, because there's a use case that isn't counted for, and then you have to upgrade because there's something else that isn't counted for. So you don't have a lot of options in terms of tooling. That's just one example that I gave that we went through, but there's been a lot others that made us realize on a different language, you would have a lot of different options to solve a problem based on your use case. And then the amount of time to be proficient, it's quite some time. I prefer to like read books and then to learn from it and to practice with it. If you're like that, you realize it does take quite some time. And if you prefer videos, maybe that's not as slow. Maybe it's a bit faster. But with Rust itself, I have found that it takes a lot of time to become proficient, and it's not so much right now, but definitely at the beginning, hiring was more difficult just because it wasn't very well known. But now, I think because of meetups like this, it's just spreading the word and the usefulness of the language. It's become a lot easier actually to hire for it. And then the wait for async, yeah, that was a pain. And even going through the refactoring of it, at the time, 10 different services all had to go through major refactoring because it's a breaking change. And there are a couple of things which will possibly breaking changes going forward as well. Hopefully not. I think the async traits is one that I'm hoping won't be, but yeah, we will see. Was it worth building it all? Yes, definitely. Mostly because of the robust nature of the language, the entire error handling of it, and also how fast and very little resources it uses. What we're looking to do next is the top of our priority is async traits. We're looking to, we currently use the async trait crate, which does give you traits with async. But it means other crates don't work together very nicely with it, especially with macros. Once you have macros together with async trait, it usually breaks the macro. And so we've had to do a lot of work to find a specific macros that work together nicely with async trait. So we're waiting for the official version of it from Rust, and that's probably the number one thing that we're looking forward to. Other things is Rust in ML, machine learning. It isn't very mature at the moment, but we are looking to use the clustering model, which is more mature compared to other parts of it. So we've been just kind of experimenting with it to see if it is something we can use, or if we have to use something else. I don't know, Python or R, or just something that's more mature. And then smart contracts. Yeah, so the whole solutions on a blockchain. So we want to, and this is very, very far out. There are a few blockchains, and Concordium being one of them, that have smart contracts that you can write in Rust. And one of the things we are looking to do, and this is something that we're not like planning immediately, but just out in the future, is to have most of our advice models on the blockchain. So it's public information, and then they can get updated and get used by others as well. But this is something for very, very far away, although there's already work in this space in Rust, and whether it's on the Polkadot or on actually it's not on Polkadot, on Mayota or a few others. They are working on it already, and there's actually they're building SDKs also on top of things like Cardano. So we're looking forward to that. And that's the end of it. I hope I didn't spend too much time on it. Yeah, okay. For any questions at all, please do let me know. I'm happy to go through it. Even if I didn't cover it, anything you would like to know in our journey, I'm more than happy to go through it as well.
Thank you, Eric. But I have a question. You kind of answered it already. So basing the whole company on Rust, how hard it is to get a talent, especially maybe what kind of stuff are you looking for? Are you willing to train from scratch, or like what kind of background are you looking for?
Yeah, I remember having a conversation with Luca. I think he had a talk here as well a couple of months ago. So he was also hiring some Rust developers for TrueLayer about a year ago. And we were both struggling to find actual developers with Rust experience. So we discussed what experience was close enough to Rust that we'll be happy to train, or will be easier for the developer to train and understand Rust. And we both had the same idea that C or C++ is probably the closest one. The main reason for that was because of the whole memory management part of it. So you have to be aware of how memory is managed. And with Rust, although you don't manage it yourself, you do have to be aware of it. So you know when you lose a variable and when you don't. So that's definitely what I would say when you write down a job description, you say ideally you want Rust experience, but you're happy if you have C or C++ experience.
Okay. There's a question, when do you think we will see a Ruby on Rails like solution for Rust?
That's an interesting question. Yeah, I was having a look at the Are We web yet a couple of weeks ago, and it's still not to that level. I think it's still a way off. It's hard to put like a direct number, like a date to it. But if it's something you're waiting on, I would say maybe start building it yourself, because it might be easier.